Having covered the residue theorem and the various methods to obtain the residues, we will now see the actual application of the theorem. Okay, we will classify the problems into two parts or two types, let us say. In the first type, we will be solving the contour integrals, meaning the integrand will be a function of a complex variable. Okay, and the second part is you can actually use this technique of residue integration to solve real integrals, meaning you can actually compute real definite integrals, of course, where the integrand is a function of real variable and the path of integration is along x-axis, okay, or the real axis. Okay, we will be covering two types within real integrals. Type 1 is when the integrand is a rational function of both sine and cosine functions. Okay, this is by far the most popular type. As far as the exams are concerned, and we do occasionally use the residue theorem for finding improper integrals. Okay, now because we have not yet covered what improper integrals are, let me remind you that there are two kinds of improper integrals. Okay, remember, now we are talking about functions of real variables. Okay, now these two kinds are respectively as follows. In the first, we have one or both limits as infinity. Okay, so you may have limits as minus infinity to a, or you may have limits as b to infinity, where both a and b are any real numbers, and you can also have minus infinity to plus infinity. Okay, so this is improper integral of the first kind. Second is that function possesses a discontinuity within the interval of integration. So in such cases, you have to split the interval of integration at the point of discontinuity. Let us say if the function has only one discontinuity at c in the interval of integration, then you actually integrate a to c, the function from a to c, and then you integrate the function from c to b. Okay, now you may be required to take the help of limits to solve these integrals. Okay, now here the word limits is being used in two different meanings. Okay, first is limits as in limits on the integral, definite integral, and second is limit of a function. Okay, so if the limit of the integrated function exists at these, then we say that the integral actually converges. Otherwise we say that the integral diverges or does not exist. Okay, now out of these two kinds, we will cover only the first one with infinite limits. You can actually apply the same technique when we have discontinuities within the interval of integration. And in addition to these two, we can also solve problems on finding inverse Laplace transform and inverse Fourier transform with the help of the residue theorem. Okay, but because we have not yet covered what Laplace and Fourier transforms are, we will not be talking about those problem types. We will be talking about only these two. Okay. The thing about Laplace transform is that, if you remember, when we were discussing the geometric series and its convergence, we talked about Z transform. Okay. Now the Z transform exists for discrete functions, which we call sequences. Okay. And the Laplace transform is actually the continuous analog of the Z transform. So here, when we find the Laplace transform of any function, it is not a sequence, it is not a discrete function, but it is a continuous function. Okay, we say that it is piecewise continuous. It may have finitely many or even infinitely many discontinuities, but should be piecewise continuous. Okay. All right. Then we also have functions like gamma functions, gamma function. Okay, which is expressed in terms of an improper integral of this kind. Okay, but we will talk about all these things at an appropriate point. The thing is, residue theorem is a versatile technique which is capable of finding many integrals which are otherwise very difficult to obtain by the techniques of real variable calculus. Okay, so let us now see the problems. Evaluate by residue theorem the integral along closed curve C of the function sine of pi z squared plus 2z divided by z minus 1 squared into z minus 2 with respect to z, where the contour C is the circle centered at the origin and radius 4. Okay. Now it is not very difficult to see that this particular function possesses two different poles. Okay. You have to just equate the denominators to 0. Okay, as far as this function is concerned. Okay. Now what is the power of z minus 2 in the denominator? The power is 1. So for the pole z equal to 2, the order is going to be 1. Okay. And because for z minus 1 the power is 2 there, the order of the pole is going to be 2. Okay. Now let us determine the location, the relative location of these two poles with respect to mod of z equal to 4. Okay. So all you have to do is you have to substitute the value in z here. Okay. So let us say we go to first. Mod 1 is 1. Is it less than 4? So this lies inside. Okay. Go to mod 2. Again less than 4. So this also lies inside C. So in order to find the value of this integral, we will find the residue at 1 and at 2. We will add the residues and we will multiply the addition by 2 pi I. That is what the residue theorem tells us. Okay, so let us do that. First, we will go to the simple pole whose order is 1, that is z equal to 2. We now recall the formula. Okay, if we take the limit and if we don't get any indeterminate form, then the residue will be z minus 2 into f of z at z equal to 2. Okay, so let us see if this works. First, we will cancel that part from f of z which consists of z minus 2. Okay, so we will be left with the function sine of pi z squared plus 2z in the numerator and z minus 1 squared in the denominator. We will be now substituting z equal to 2 there. Okay, so do it. Sine of 4 pi, sine of pi z squared plus 2 times z, so 2 times 2, so 4. Okay, and in the denominator we will have 2 minus 1 squared, which is 1. Okay, sine 4 pi 0. So the residue at z equal to 2 is 4. And now you may realize this, that finding the Laurent series of this particular function may take us a lot of time, right? Because of presence of the trigonometric function sign in addition to the polynomial functions. Okay, all right. Now we have calculated the residue successfully at z equal to 2. Now to find the residue at z equal to 1, which is not a simple pole but a pole of order 2, we will use the formula which we developed for poles of higher order. Okay, so here k is 2 in our usual notation. So the residue at z equal to 1 will be 1 upon k minus 1 factorial into k minus 1th derivative of the function multiplied by z minus z naught to the power k evaluated at z equal to 1. Okay, 1 upon 1 factorial is 1, so leave it. Do not forget to multiply the given function by z minus 1 squared. Okay, all right. So this will lead to the cancellation of that factor in the denominator. And now perform the differentiation process. Okay, simple division rule. Derivative of the numerator, cos of pi z squared into 2 pi z plus 2, second function as it is, minus first function as it is, sin of pi z squared plus 2z into derivative of the second function or denominator, which is 1, divided by square of the denominator. And remember, we are finding it at z equal to 1. Okay, don't forget this. So now what remains to be done is the substitution of substitution of z by 1. Okay, so let's put it everywhere. First term will be cos of pi, which is minus 1, into 2 pi z, so into 2 pi, so minus 2 pi, keep this as it is, into minus 1. Okay, so 1 minus 2, so minus 1, minus sin of pi z squared, sin pi 0, so this will just be minus 2 because of the negative sign that is present outside. In the denominator it is going to be square of minus 1, so plus 1. Okay, now let us simplify this. Minus 2 pi into minus 1 is 2 pi, plus 2 into minus 1 is minus 2, and then again we have got this minus 2 here, and in the denominator we have got 1, so it is 2 pi minus 4. Okay, we have successfully calculated the residues. Let us now add them and multiply the addition by 2 pi I. Okay, the residue due to z equal to 2 or at z equal to 2 was 4. Yes, and the one that we have computed here, 4 pi minus 4, well, not 4 pi minus 4, sorry, 2 pi minus 4, this is at z equal to 1. So just add them, you will get 2 pi I into 2 pi, so it is 4 pi squared I. Okay, so this is how we solve problems on contour integrals using the residue theorem. Now it may be interesting to change C. Okay, for example, let me take C to be the circle mod of z equal to 1 upon 2. Okay, if I take the circle mod of z equal to 1 upon 2, then both z equal to 2 and z equal to 1, both these poles lie outside. Okay, which then means that we can now apply the Cauchy's theorem, and hence the value of the integral would be 0 because it is analytic on and inside C. Okay, if I now change C and if I take it as mod z equal to 3, then z equal to 2 lies outside. Sorry, I should change it. Okay, instead of 3, suppose I take mod z equal to 3 by 2. Okay, yeah, this works. So then z equal to 2 will be outside, but z equal to 1 will be inside. Okay, So in this case, what is going to be the value of the integral? The value of the integral will be 2 pi I into the residue only at z equal to 1, which is 2 pi minus 4. Okay, and if we now consider the following situation, mod of z minus 2 equal to 1 upon 2. Okay, so now the pole z equal to 2 is inside, but z equal to 2 is outside. So what will the value be? The value of the integral will now be 2 pi I times the residue at 2, which is 4. So the integral's value would be 8 pi I. Okay, so depending on the locations of the poles with respect to the contour C or the curve of integration, we will go on getting different values of the integral. Okay, let us now see one more example. Question 2. Integrate tan z with respect to z along a curve C, which is given by mod of z equal to 2. So again a circle centered at origin, radius 2. Now we know that tan of z has infinitely many singularities. Okay, you can prove that all singularities are simple poles for tan z. That means there is only going to be one term in its Laurent series. Well, there will only be one term in its singular part, okay, or the principal part, which is going to be 1 upon z minus that singularity, okay, into b1 of course, and we are going to find b1 now. But first we need to determine how many of those poles lie inside C. Okay, now it is mod of z equal to 2 and pi is approximately 3.14. So pi by 2, the first point pole is approximately 1.57, but the moment you go to 3 pi by 2 it exceeds 2. Okay, so we need to consider only two of them. Both are on real axis, z equal to pi by 2 and z equal to minus pi by 2. Okay, yes. So can we now determine the residue at z equal to pi by 2? Very easily. See, this time we are required to take the limit, okay, because this is now in the 0 by 0 form. Z minus z naught into f of z. Okay, so once you apply the L'Hospital's rule, take the derivative of the denominator first. It is simple. Derivative of cos is negative sign. Apply the product rule to find the derivative of the numerator. Z minus pi by 2 is derivative 1, second function as it is, plus first function as it is into derivative of the second function, that is derivative of sine, which is cos. Okay, substitute z equal to pi by 2 now, and because we have negative sine z, it won't be in the indeterminate form. Due to z equal to pi by 2, second factor will be 0, second term, first term will be 1, 1 upon minus 1 is minus 1. So residue at z equal to pi by 2 is minus 1. Okay, and because, so to speak, this is an even function, cos is even and product, is it even? Well, let's find out. I think it is an even function. Yeah, you can find the residue at z equal to minus pi by 2. So this time you are required to multiply the function not by z minus pi by 2, because z naught itself is minus pi by 2, it will be z plus pi by 2. Okay, fine, so let's do it. Is it in the indeterminate form? Yes, again it is in the indeterminate form, so you can actually find the derivative of the numerator and of the denominator, and you will get the value as negative 1. Okay, fine. So we will do it for this. There is no question of the denominator. Okay, the denominator is going to be minus sine z, so I think it is going to be 1. Yes, minus sine z. Let's take the derivative of the numerator, which is going to be 1 times sine z, so minus 1, plus, yeah, this is anyways going to be 0, so minus 1. Okay, correct. So we have now successfully computed the residues at pi by 2 and minus pi by 2. Let's now add them, which will give us minus 2, and therefore the value of the integral will be 2 pi I times minus 2, or minus 4 pi I by residue theorem. Okay, now let us go to one more question. This is from your exams. Okay, question 3. Evaluate the integral e to the power pi I z upon 2z squared minus 5z plus 2 with respect to z along gamma, where gamma is the unit circle mod of z equal to 1 that orients counterclockwise. Okay, we will first write down the integrand. The integrand is e to the power I pi z, or pi I z upon 2z squared minus 5z plus 2. Now, what I would recommend is, whenever you are factorizing the denominator, to look for its zeros, which will then become the poles of the original function. You always make sure that the coefficient of the highest degree term is 1. Okay, so it sometimes produces incorrect answers. So if you do that, it is going to be 1 upon 2 times same numerator, but denominator will now be z squared minus 5 by 2z plus 1. Okay, yes, this is now very easy to factorize. For poles, you have to solve this quadratic equation, apply the quadratic formula, or you can even use your calculator now to get the roots. The roots will be 2 and 1 upon 2. Let us just verify them. The product has to be c by a, which is 1, and product here is 2 into 1 upon 2, so 1. Addition has to be minus b by a, which is 5 by 2, and the addition of these roots is again 5 by 2. Yes, okay. Now let us see, let's try to find out the location of these two poles. Okay, you observe that this thing can be factorized as z minus 2 into z minus 1 upon 2. So both are simple poles, meaning their order is 1. Okay, now let us determine the relative locations. This is our unit circle. Both the poles are real. Z equal to 2 will be here, so outside, and z equal to 1 upon 2 will be here, so inside. Okay, so are we required to compute the residue at 2? No, not required for this. If it had been a curve which includes z equal to 2 in its interior, then we would be required to add the residue at 2 to the residue at 1 upon 2. Okay, so the relative locations are z equal to 2 outside and z equal to 1 upon 2 inside. So only consider the pole at 1 upon 2. Okay, yes, so it is always good to first write the integrand in such a form so that the poles can be very easily identified, and then you can start applying the residue theorem. Okay, so what I'll do is I'll keep 1 upon 2 as it is. Now this integral is now going to be 2 pi I times the residue at simply 1 upon 2. Why 1 upon 2? Because although z equal to 2 is a simple pole, it lies outside. Okay, so there's no need to calculate the residue there. 2 will get cancelled, so you will have pi I into residue at z equal to 1 upon 2. Put z as 1 upon 2 in the remaining part. Okay, so the denominator will be 1 upon 2 minus 2, which is negative 3 by 2, and this is now e to the power I pi by 2, which is I. Okay, use the Euler's formula. which is cos pi by 2 plus I sin pi by 2, cos pi by 2 0, sin pi by 2 1, so e to the power I pi by 2 is I itself. Okay, so this is I pi times I upon minus 3 by 2, I squared is minus 1, so it is 2 pi by 3. Okay, now the feature of this particular integral is that its value is a real number. Okay, although the function was a function of complex variable z, and the contour which we were along which we were integrating had only 2 points which were purely real, minus 1 and 1. Everything else had or has non-zero imaginary part, but still the value of the integral is real. Okay, and this is going to happen quite a few times in the residue theorem problems. Okay, or in general integration, the integrals along any closed curve in the complex plane. Okay, so now we have solved 3 problems where the function was a function of complex variable and the contour of integration was a closed contour in the complex plane. Let us now switch to the evaluation of real integral.